Hello students, as we have studied in the previous section what is momentum thickness, energy thickness and boundary layer thickness. Along with that we have seen what is displacement thickness and von Karman's momentum integral equation. So let us apply all these concepts to solve problems on boundary layer theory. So we have a problem over here which states that the velocity distribution for a laminar flow is u upon u infinity, which is given as sine pi by 2 y by delta. So this is what is the equation which is given to us. Note that the purpose of solving this problem is for solving this as a trigonometric equation. So the boundary layer thickness is delta is equals to, we have to calculate what is boundary layer thickness. Delta is a function of Reynolds number, drag force, shear stress as well as coefficient of drag. All these things we have to calculate. So now we'll be solving this problem. First, for solving this problem we'll need what is boundary layer thickness. So in terms of Reynolds number, for that we have to apply von Karman's energy momentum integral equation. So let us apply this von Karman's momentum integral equation. For that we need what is momentum thickness. So first we'll write von Karman's momentum integral equation. Von Karman's this states that tau is equals to rho into u infinity square dou theta by dou x. So this is what is the equation. For that we need what is momentum thickness. So momentum thickness we already know, that is 0 to delta u upon u infinity into 1 minus u upon u infinity into dy, where u upon u infinity is given as a sine of pi by 2 times y by delta. So let us substitute in this equation. So the momentum thickness theta is integral 0 to delta sine of pi by 2 y by delta into 1 minus sine of pi by 2 y by delta into dy. So this is the equation. Let us use substitution method over here to solve this integration. So let y by delta is equals to x. So we'll get dy is equals to dx into delta, and when y is equals to 0, x is also equals to 0, and when y is equals to delta, x is equals to 1. So we have all these terms, we'll substitute in this equation. So we'll get this theta is equals to integral 0 to 1 sine of pi by 2x into 1 minus sine of pi by 2x into dx into d delta. So we have to solve this equation. To solve this equation, I'll give you a shortcut technique uh, that is directly solving this equation in your calculator. So now we'll use our calculator over here. So in this part, we have to put an integration of, we have to substitute this term, that is a function is a sine, that is integration of sine pi into x by 2 into bracket of 1 minus sine into pi x by 2. There are two brackets over here, so we'll close both the brackets and we'll substitute this from 0 to 1. Note that over here this is in radian mode. How to switch between radian mode, that is shift and mode setup, you have to press 4, that will be in the radian mode. Once you convert this into radian mode, press equals to, directly we'll get what is the answer of this equation. So this answer will take a short bit of time, but we have got this as 0.1366. So we have got this answer of theta as 0.1366. I'll just write down over here, note, that is convert calculator from degree mode to radian mode and calculate. So we have got this is times delta, since this is the integration we have substituted, and delta is the boundary layer thickness. So now let us substitute in this von Karman's equation. So tau is equals to one part, this is rho into u infinity square dou theta by dou x. So this is rho into u infinity square dou by dou x of theta. This is 0.1366 times delta. So this is rho into u infinity square 0.1366 into dou by dou x of delta, that is value of tau 0. So this is one of the right hand side of the equation. The left hand side of the equation, that is tau 0, which we can calculate by Newton's law of viscosity. So according to Newton's law of viscosity, we know that tau 0 is equals to mu into du by dy at y is equals to 0. So let us calculate what is du by dy. So this is equals to, we have to substitute for y for this function, that is u upon u infinity is equals to u times sine pi by 2 y by delta. So over here u is equals to u infinity into sine pi by 2 y by delta. Let us differentiate this. Du by dy is equals to u infinity into this integration of sine is cos pi by 2 y by delta into pi by 2 by delta. So we have to substitute this entire part at y is equals to 0. So we have to substitute this part as a 0. So we'll get this entire part as cos 0, which will be 1, and we'll get this as a dy du by dy at y is equals to 0, that is u pi by 2 times delta. Now note that this is greater than 0, hence there is no boundary layer separation. U infinity is greater than 0, delta will be also greater than 0. So this is greater than 0, so there is no boundary layer separation. So let us substitute this in Newton's law of viscosity. So we'll get this equation as tau is equals to mu into u infinity pi by 2 delta, and tau is also equals to, according to von Karman's equation, which we have seen in the previous part, that is a rho into u infinity square into 0.1366 into dou by dou x of delta. So we have these two equations. We'll substitute one in terms of other. So this is a rho into u infinity into 0.1366 into dou delta by dou x into mu into u infinity pi by 2 into delta. So over here value of u infinity and this value will go away, and we can calculate the entire thing. So let us take all the terms considering delta on one side and all the x terms on the other side. All these terms other than delta and x are constant. So over here we'll write this part as equals to dou delta into delta will be equals to, this part will be equals to, let us take on all the terms on one side. So this will be mu into pi by 2, delta is gone on the other side, upon a rho into u infinity into 0.1366, so into dou x. So this equation we have got. So on integrating this part, so what we'll get this as delta square by 2, so and multiplying this and along with pi, the constants will be equals to 11.5 into mu upon rho into u infinity into x plus c. So all the terms we have considered over here. So now over here we'll substitute the condition of trailing edge, so leading edge, pardon me. So at condition of leading edge, at a leading edge point, we have x is equals to 0, y is equals to 0, delta is equals to 0, and hence we'll get delta square by 2 is equals to 11.5 mu upon rho into u infinity. Now we have to take this on the other side and take the square root, and rather this will be multiplied by x. So delta is equals to square root of 11.5 into mu upon rho into u infinity. Just to convert this into Reynolds number, we'll multiply by x. X is there initially, into x, divide by x. So this entire equation becomes the Reynolds number, and this will be value of x square. So delta will be equals to square root of 11.5 upon Reynolds number into x square, which will give us 4.796 x upon square root of a Reynolds number. So we have got this entire part in terms of Reynolds number. So which was the first part, that is the boundary layer thickness in terms of Reynolds number. Second thing which we'll calculate is the shear stress. Now we already know that tau is equals to, that is shear stress, according to Newton's law of viscosity, tau is equals to mu u infinity into pi by 2 into delta. So this is the value which we have got. Let us substitute the value of delta in this equation. So over here tau 0 is equals to mu into u infinity pi by 2. Delta has a value of 4.796 times x upon a Reynolds number, that is Rex. So let us substitute this. So tau 0 is equals to mu into u infinity upon 2 into pi into 4.796 times x into square root of Rex. So this is the value of mu. So on evaluation of these all terms, so we get this as a tau 0 will be equals to, the constant part is a 0.237 mu into u infinity into square root of Rex upon x. So this is value of shear stress. Now let us calculate what is force due to drag. So that is drag friction or drag force. So the drag force can be written as, Fd is equals to integral 0 to L tau v into dx. So on substituting the value of tau, we'll get this as Fd is integral 0 to L, value of tau is 0.327 mu into u infinity upon x into square root of Rex b into dx. Now value of x is in both the equation, so we'll split this part, that is Fd is 0 to L 0.327 into mu u infinity into square root of rho u infinity x upon mu upon x into b into dx. So over here this x and this x will be square root of x. Let us consider this entire portion as value of k and let us integrate this. So need not to write all over again. So integral 0 to L k x raised to minus 1 by 2 into dx. So this value which we have got. So when we'll integrate this, so fd will attain the value of k into L raised to 1 by 2 divided by 0.5, which is 1 by 2 over here. So the value of k will resubstitute, the constant will change, so we'll get this value of fd is equals to 0.655 mu into u infinity into square root of rho into u infinity upon mu into L raised to 1 by 2, the whole thing divided by 0.5, so or 1 by 2. So this when it is divided by this part, fd will give us as equals to, rather we have divided this, so this is 0.655 mu into u infinity into square root of rel. Note that here it should be it is not 1.1 by 2 because we have actually multiplied directly over here, then only we'll get that is 0.655. So fd we have got the value that is in terms of Reynolds number. Now and this value will be of course multiplied by b. Here also this is multiplied by b. Now we have to calculate what is average coefficient, not average, rather coefficient of discharge. So we know that coefficient of discharge is given by fd upon half a rho a into u infinity square. So this is what is coefficient of discharge. So this is equals to 0.655 mu into u infinity into square root of rel into b upon half rho b into L, that is area, into u infinity square. So over here these two parts will go away, b and b will go away, and over here in the Reynolds number we will have some value of L, but we'll keep as it is. Over here we have rho u infinity L and mu, so we'll convert that into Reynolds number and this will be multiplied by 2, so we'll get this part as CD will be 1.31 upon Reynolds number into square root of REL. So CD will be equals to 1.3 upon square root of REL. So we have calculated what is coefficient of discharge, we have calculated what is shear stress, as well as we have seen what is boundary layer thickness as a function of Reynolds number, and lastly we have seen whether the boundary layer separation will take place or not. So I hope you have understood the evaluation over here which we have done in this problem. And the most important thing about trigonometric problem is we have to convert our calculators from degree mode to radian mode in order to solve these kind of problems. Thank you.